Ground loop impedance typically refers to the impedance of the electrical path formed by an unwanted current loop between the electrical system and the ground. This current loop can occur in both alternating current and direct current systems. In alternating current systems, ground loop impedance is particularly important because it can cause ground currents to flow, which can lead to electrical hazards such as shocks, fires, and equipment damage. The impedance of the ground loop path is measured in ohms and is influenced by factors such as the resistance of the grounding conductors, the inductance of the electrical cables, and the capacitance between different parts of the system. Ground loop impedance is also present in direct current systems, although it is generally less critical than in alternating current systems. In direct current systems, ground currents can flow due to differences in potential between different parts of the system. However, the presence of a ground loop impedance can help to limit the magnitude of these currents and prevent potential hazards. Yes, direct current grounding exists and involves impedance. Direct current grounding is the process of intentionally connecting the negative terminal of the direct current power supply to the electrical ground. This is done to ensure that any straight currents or faults are safely directed to the ground, reducing the risk of electrical hazards. The impedance of the direct current grounding path is crucial for safety. Ideally, the impedance should be as low as possible to ensure that any fault currents can flow easily to the ground and trip the circuit breakers or fuses. The impedance is affected by factors such as the resistance of the grounding conductors, the inductance of the grounding path, and the grounding electrode's characteristics. Ground loop impedance is a term that applies to both alternating current and direct current electrical systems. It refers to the impedance of the electrical path formed by an unwanted current loop between the system and the ground. Grounding in direct current systems also involves impedance, which is important for ensuring the safety and proper operation of the system. It is important to understand the factors that contribute to ground loop impedance in both alternating current and direct current systems, and to take steps to minimize its impact on electrical safety and performance. In alternating current systems, the impedance of the ground loop is affected by several factors, including firstly the resistance of the grounding conductors. The grounding conductors are the wires that connect the electrical system to the earth ground. The resistance of these conductors can vary depending on their size, material, and length. Higher resistance grounding conductors will increase the impedance of the ground loop. Secondly, the inductance of the electrical cables also plays a role. Electrical cables have inductance, which is a measure of their ability to store energy in a magnetic field. The inductance of the cables can increase the impedance of the ground loop, especially at higher frequencies. Thirdly, the capacitance between different parts of the system can also affect the ground loop impedance. Capacitance is a measure of the ability of a system to store electrical charge. Capacitance between different parts of the system can create unwanted current paths, which can increase the impedance of the ground loop. In direct current systems, the impedance of the ground loop is also affected by several factors, including firstly the resistance of the grounding conductors. As in alternating current systems, the resistance of the grounding conductors can increase the impedance of the ground loop. Secondly, the inductance of the grounding path is important. The grounding path is the path that current takes from the electrical system to the earth ground. The inductance of this path can increase the impedance of the ground loop, especially at higher frequencies. Thirdly, the grounding electrode's characteristics also matter. The grounding electrode is the metal rod or plate that is buried in the earth and connected to the grounding system. The characteristics of the grounding electrode, such as its size, material, and depth, can affect the impedance of the ground loop. To minimize the impact of ground loop impedance, several steps can be taken in both alternating current and direct current systems. Firstly, use grounding conductors that are of adequate size and material. The grounding conductors should be sized according to the relevant electrical codes and standards. They should also be made of a material that has low resistance, such as copper. Secondly, minimize the length of the grounding conductors. The longer the grounding conductors, the higher their resistance will be. Therefore, it is important to minimize the length of the grounding conductors as much as possible. Thirdly, avoid creating ground loops. Ground loops are created when there are multiple paths for current to flow to ground. This can increase the impedance of the ground loop and create unwanted currents. To avoid creating ground loops, ensure that there is only one path for current to flow to ground. Fourthly, use shielded cables. Shielded cables have a conductive shield that surrounds the conductors. This shield can help to reduce the amount of electromagnetic interference that is coupled into the cables, which can reduce the impedance of the ground loop. Fifthly, use isolation transformers. Isolation transformers are transformers that isolate the electrical system from the earth ground. This can help to prevent ground currents from flowing and reduce the impedance of the ground loop. In direct current systems, it is also important to ensure that the grounding electrode is properly installed. The grounding electrode should be buried deep enough in the earth to ensure that it is in contact with moist soil. The grounding electrode should also be made of a material that is resistant to corrosion. In addition to these general steps, there are also some specific steps that can be taken to minimize the impact of ground loop impedance in alternating current systems. Firstly, use a star grounding configuration. In a star grounding configuration, all of the grounding conductors are connected to a single point, which is then connected to the earth ground. This can help to reduce the impedance of the ground loop and prevent ground currents from flowing. Secondly, use a ground fault circuit interrupter, commonly known as a GFCI. A ground fault circuit interrupter is a device that detects ground faults and interrupts the flow of current. This can help to protect people from electrical shocks and prevent fires. In direct current systems, it is also important to ensure that the direct current power supply is properly grounded. The direct current power supply should be grounded according to the manufacturer's instructions. This can help to prevent ground currents from flowing and reduce the impedance of the ground loop. Ground loop impedance is a complex topic, but it is important to understand its impact on electrical safety and performance. By taking the steps outlined above, it is possible to minimize the impact of ground loop impedance and ensure that electrical systems are safe and reliable. Let's delve a bit deeper into some aspects. Firstly, let's cover the significance of low impedance grounding. Low impedance grounding is crucial for electrical safety and equipment protection. It ensures that fault currents can quickly and safely return to the source, tripping protective devices like circuit breakers or fuses. This rapid response minimizes the duration of the fault, reducing the risk of electrical shock, fire, and equipment damage. A high impedance ground, on the other hand, can impede the flow of fault current, delaying the activation of protective devices and increasing the potential for hazards. Secondly, it is essential to properly size grounding conductors. Grounding conductors must be sized according to applicable electrical codes, such as the National Electrical Code, or NEC. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. Properly sized grounding conductors provide a low impedance path for fault current, ensuring that protective devices operate correctly. Undersized grounding conductors can have excessive impedance, hindering the flow of fault current and compromising safety. Thirdly, we need to understand the role of grounding electrodes. Grounding electrodes, such as ground rods or ground plates, provide a connection to the earth, which serves as a reference point for the electrical system. The earth has a relatively low impedance, allowing fault currents to dissipate safely. Grounding electrodes must be installed correctly to ensure good contact with the earth. Factors such as soil type, moisture content, and electrode depth can affect the effectiveness of the grounding electrode. Regular inspection and testing of grounding electrodes are essential to verify their integrity. Fourthly, let's analyze the impact of inductive reactance. Inductive reactance is the opposition to the flow of alternating current caused by the inductance of conductors. Inductance is present in all electrical conductors, but it becomes more significant at higher frequencies. Inductive reactance increases the overall impedance of the ground loop, which can impede the flow of fault current. To minimize inductive reactance, grounding conductors should be kept as short and straight as possible. Using multiple parallel grounding conductors can also reduce inductive reactance. Fifthly, we consider the effects of capacitive reactance. Capacitive reactance is the opposition to the flow of alternating current caused by the capacitance between conductors. Capacitance can exist between grounding conductors and other conductive objects such as metal enclosures or equipment frames. Capacitive reactance can also increase the overall impedance of the ground loop. To minimize capacitive reactance, grounding conductors should be kept as far away as possible from other conductive objects. Using shielded cables can also help to reduce capacitive reactance. Sixthly, we should understand the concept of equipotential bonding. Equipotential bonding is the practice of connecting all metal parts of an electrical system together to create a common ground potential. This minimizes voltage differences between different parts of the system, reducing the risk of electrical shock. Equipotential bonding is particularly important in areas where people are likely to come into contact with metal objects, such as bathrooms and kitchens. Seventhly, we should know how to test ground loop impedance. Ground loop impedance can be measured using a ground loop impedance tester. This device injects a small current into the grounding system and measures the voltage drop across the ground loop. The impedance is then calculated using Ohm's law. Ground loop impedance testing should be performed regularly to verify the integrity of the grounding system. High ground loop impedance indicates a problem with the grounding system that needs to be addressed. Eighthly, we should explore mitigation techniques for ground loops. Ground loops can cause a variety of problems, including noise, hum, and interference. There are several techniques that can be used to mitigate ground loops, including firstly, breaking the ground loop by isolating the ground connection at one point. Secondly, using differential amplifiers, which are less sensitive to common mode noise. Thirdly, using optical isolators, which provide electrical isolation between different parts of the system. Ninthly, we should discuss grounding in sensitive electronic equipment. Sensitive electronic equipment, such as computers and audio equipment, is particularly susceptible to ground loop problems. To minimize ground loop problems in sensitive electronic equipment, it is important to firstly, use a dedicated grounding conductor for the equipment. Secondly, avoid connecting the equipment to multiple ground points. Thirdly, use shielded cables to reduce noise and interference. Tenthly, we should cover regulatory standards for grounding. Grounding is regulated by various electrical codes and standards, such as the NEC in the United States and the IEC in Europe. These codes and standards specify the requirements for grounding systems, including the size of grounding conductors, the installation of grounding electrodes, and the testing of ground loop impedance. Compliance with these codes and standards is essential for electrical safety. Ground loop impedance is a crucial concept in electrical engineering, impacting both safety and equipment performance in AC and DC systems. Understanding the factors influencing it, such as conductor resistance, inductance, and capacitance, is vital for designing and maintaining effective grounding systems. Implementing mitigation techniques, adhering to regulatory standards, and conducting regular testing are key to ensuring electrical safety and minimizing the risks associated with ground loops. Furthermore, consider the practical implications of impedance in different scenarios. For instance, in a data center, a robust grounding system with low ground loop impedance is paramount to protect sensitive electronic equipment from damage due to voltage fluctuations and stray currents. Similarly, in industrial settings with heavy machinery, a well-designed grounding system ensures the safe dissipation of fault currents, preventing electrical hazards for workers. In residential buildings, proper grounding safeguards against electrical shocks and reduces the risk of fire caused by faulty wiring. The principles of ground loop impedance also extend to renewable energy systems, such as solar panel installations. In these systems, grounding is essential for protecting against lightning strikes and ensuring the safe operation of the inverter, which converts direct current from the solar panels to alternating current for use in the home or grid. Grounding considerations also play a crucial role in automotive electrical systems. Modern vehicles rely heavily on electronic control units, or ECUs, and sensors which are sensitive to electrical noise and interference. A properly grounded chassis and electrical system minimize ground loops and ensure reliable operation of these components. In aerospace applications, where weight is a critical factor, careful selection of grounding conductors and bonding techniques is essential to minimize weight without compromising electrical safety and performance. The principles of ground loop impedance also apply to medical equipment. In hospitals and clinics, it is essential to protect patients and staff from electrical hazards. Medical equipment must be grounded properly to ensure that any leakage currents are safely directed to ground, minimizing the risk of electrical shock. In telecommunications infrastructure, grounding is essential for protecting equipment from power surges and lightning strikes. Telecommunications towers and equipment are often located in exposed areas, making them vulnerable to these hazards. A well-designed grounding system can help to dissipate these surges and protect equipment from damage. Therefore, the concept of ground loop impedance is not just a theoretical one, but has practical implications in various fields and applications. A thorough understanding of ground loop impedance and its related principles is essential for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems. It is also crucial to stay updated with the latest electrical codes and standards to ensure that grounding systems are implemented correctly and meet the required safety regulations. Continuous learning and professional development are important for staying abreast of the latest technologies and best practices in grounding and electrical safety. In conclusion, the intricacies of ground loop impedance span across alternating current and direct current systems, demanding a comprehensive understanding for ensuring safety and optimal performance. From residential homes to complex industrial setups, the principles of grounding and impedance management are fundamental to protecting both people and equipment.